Good afternoon, everybody. It's a great pleasure to have today with us Professor Andrea Macciò. I've known Andrea for 20 years, I think, when he started his first postdoc in Zurich at the University of Zurich, and I was finishing my PhD. Yeah. Okay. Anyway, Andrea graduated in Milan with Professor Borrometto, right? And then also made his PhD in Milan, and then he worked on gravitational lensing, and then he moved to Zurich, and there he worked with Professor Ben Moore, and then he was in Zurich for 3 years, roughly, yeah. And then he went to Heidelberg at the Max Planck Institute for Astronomy, where he was an independent group leader and started to work on galaxy formation. And now he's a professor at the New York University of Abu Dhabi, and he's also the director of the Research Center of Astroparticle and Planetary Physics. And he was also the dean of the Department of Physics in Abu Dhabi. And today, yes, he's going to talk about the dark matter, and I think he will make a review about the current status. Thank you very much. Please.
Thank you, Luigi, for the nice introduction. Yes, it's indeed 20 years we know each other. Time flies. So what I want to talk today about is there any need to explore models of dark matter which are more complex than the simple cold dark matter? I always start my talk discussing where I am, since my affiliation is New York University Abu Dhabi, and some people might be confused. So Abu Dhabi is the little red dot that you see down there. And if I zoom in, that's here you see here the United Arab Emirates, that's where Abu Dhabi is. I used to make jokes that it's very close to Qatar, where there might be some interesting sport competition in the fall, but now I don't do that anymore for obvious reasons. So this is a nice view of Abu Dhabi. That's Corniche. It's a beautiful place. It's a city, it's on the sea. It's very safe, very nice. And NYUAD, there's a few pictures of our campus. It's a separate campus of New York University, which is located in Abu Dhabi. And it's a very interesting place to be. It's, I think, the most diverse and international university in the world. Just to give you an idea, we see in this map, whatever is purple are countries from which we have students in Abu Dhabi. And just to give you an idea, one of my students, she comes from the Tonga Islands. Okay, so it's very interesting, and there are more than 100 languages spoken on campus. This, of course, is very rich. It's also a challenge if you try to teach physics. So the next question usually is why there is a New York University in Abu Dhabi, but that's a very separate story, which I'm happy to discuss after the talk or by email if people are interested. The last thing I want to bring up that we created a new center that I have the pleasure to direct, the Center for Astroparticle and Planetary Physics. And this center offers many opportunities for visitors, sabbatical, exchange students. So please reach out to me if you have any interest to build something with our research center. Okay, let's go back into business. That's a night sky. And since several years, we have a quite good idea of what the universe is made of. Dark matter, dark energy, and atoms. And I think you're all familiar with this pie chart. This one comes from the Planck cosmology. I think it's quite remarkable at the precision at which we know the cosmological parameters, right? We know them up to almost 1 part in 10,000. Look how small are the error bars. Now, that seems, for young people, this is quite normal, but I mean, I'm sure Fabio remembers that till a few years ago, 20 years ago, when people were presenting papers, they were discussing not just different values of those numbers, but completely different models. This is a model, this is a paper from Matthias Partmann, 1998, in which he's discussing lensing and simulations. And what you see are the 4 models he's presenting. And the first thing you notice that there is no significant digit after the first one, so 0.3, 0.7. And second, that the kind of models that people were looking at were very, very diverse. So for this reason, people tend to say that we live in the precision cosmology era. But I have a question mark there, because sometimes I wonder if this is real precision cosmology or it's just a precise measurement of our ignorance. Why I'm saying that? Because if you think about our knowledge of what dark matter is, we are stuck to 1998. Okay, our understanding of dark matter is the same that we had 20-something years ago. It hasn't really proceeded much since then. So our leading model for dark matter is called the cold dark matter model, and it has three simple properties. It starts that it's cold, so after the Big Bang, there is no real velocity in those particles. All the velocity of the dark matter particle comes from gravitational collapse. It only interacts via gravitation, so it's dark. And it's collisionless, so it has zero cross-section. When two dark matter particles meet, they just pass through each other. That's, I think, is the simplest model that people can build. And with this model, we can easily explain structure formation. This is a movie. You have a large-scale structure on the left, 50 megaparsec, a zoom in on the right of 200 kiloparsec. The zoom in, it doesn't come from this simulation. This is a different simulation. And what you see here is that how we think structure formation proceeds. It's a bottom-up process, so you first form small structures, the small structures collide, and then they form large structures. So the plot on the right is the formation of the dark matter halo of the Milky Way, our own galaxy, so it's 10 to the 12 object. And you see that, as you expect in gravity, you have a central high concentration in the object, and then you have a plethora of smaller structures, which usually referred as satellites, that zip around the dark matter halo. Some of them get destroyed when you go to the center, some of them survive. T ratio 0. Now, this model is very simple, but usually when people present it, they always say two things. The first one is that cold dark matter is very successful to large scales. And I'm sure if people work in the field have heard this sentence many times, but it faces challenges on small scales. As I always tell my students, there is no small and big in physics, so you always have to quantify. So small scales for me is 1 to 10 kiloparsec. And large scales is anything beyond 1 megaparsec. And all those problems that cold dark matter faces, they have been given fancy names through the years. So we have the missing satellites problem, diversity of rotation curves, too big to fail, Korsakoff's dilemma, galaxies without dark matter. But what I want to bring to you today is that all those problems, they actually can be grouped in one single issue. So usually those problems are at the beginning of any paper that talks about alternative theory that says, oh, we have these problems, hence we need to look for different models for dark matter. Is that really true? So all cold dark matter issues come from a very simple fact. It's very easy to understand. Dark matter halos are self-similar. Or, if you prefer, there is no scale in gravity. Gravity problem is a scale-free problem. What does it mean are self-similar? It means if I show you this is a density map of a dark matter halo, you cannot tell me what you're looking at. By no means. This object could be a galaxy cluster, something with a mass of 10 to the 14 and roughly 1,000 galaxies. Could be a group, something with a mass of 10 to the 13 and maybe 10 to 15 members. Could actually be our own Milky Way halo. That means an object with roughly 15 to 30 satellites going around. Or it could be a dwarf galaxy. Something which is extremely low density. Okay. And if you look at the bright parts from cluster to dwarf galaxies, there are something like 8 orders of magnitude in stellar mass difference. Yet the dark matter halo looks exactly the same. And this self-similarity transfers in some issues, some properties. The first one is that all dark matter halos have the same density profile. So if you plot density versus radius, you always get this specific slope, sometimes called Navarro-Frankenwide. Doesn't really matter. And this means, for example, that if you have a lot of dark matter halos, and usually instead of density profiles, it's easy to talk about rotation curves. If you have a mass and a radius, so a density and radius, you can really build the velocity out of it, gm over r. And so I rather prefer to talk about circular velocities. What you see here is a family of circular velocities that scans almost 3 orders of magnitude in dark matter mass. And of course, they're all separated. But if you rescale this radius and circular velocity, the x and the y, by some parameters, like, for example, the virial radius and the virial velocity, all those lines, they collapse on roughly a single line. Okay, that's a self-similarity. It means that no matter what you're looking at, you expect the circular velocity profile to be always the same, because it's embedded in dark matter. The problem is also for substructure. For example, regardless of which halo mass you look at, if you normalize at the mass of the central object, there are always around 300 subhalos, satellites, with a mass between 1% and 0.01%, so 10 to the minus 2, 10 to the minus 4 of the mass of the central object. So the number of satellites, it's the same if you just rescale by the mass, regardless what you're looking at. That could be 10 to the 14, 10 to the 8, doesn't matter. So why is this a problem? Well, the problem is that galaxies are not self-similar. And that's where all the problems with dark matter come about. If I look at galaxies, I don't see rotation curves that look always the same. So what you have in this plot on the left, you have observed rotation curves. Those are the points with the arrow bars. They come from the Spark survey. And what you see that those rotation curves, they have different slopes. For example, if you look here at the purple one, so the bottom right, it rises steeply, rises slowly, and then reaches a plateau. Where if you look at the green one, it rises very steeply, and then reaches the plateau much earlier. Now, you can imagine that those rotation curves cannot be fitted by a model like cold dark matter, which has only one slope and only one. Okay? So galaxies are not self-similar, and that's where all the problems come about. The same is also for substructures, because I told you that there's always this roughly 300 subhalos. The problem is that if I look now at real objects, at the Milky Way and the galaxy cluster, in the Milky Way, there are roughly 50 satellites around the Milky Way, but I have 700 satellites around Abell 1689 within the same rescaled radius. And again, cold dark matter will always predict the same number of substructures. Doesn't matter, doesn't care if it's a cluster and it's a dwarf galaxy, blah, blah, blah. So that's the problem. That's the real problem that cold dark matter is facing, is a scale-free model. Okay, so you have to break the self-similarity, otherwise you don't go anywhere. So how do you break the self-similarity? Well, one option is to touch the dark sector. So you bring a scale into the problem. For example, you have self-interacting dark matter. In self-interacting dark matter, you bring in a cross-section. Cross-section is a scale, and then it's going to break the self-similarity. Another option is what is called axion dark matter or fuzzy dark matter, which is quite popular now. Those are particles that have extremely light, 10 to the minus 23 electron volt. And what happens is that the de Broglie length, the quantum scale, becomes of astrophysical interest. So it becomes of the order of 100 parsecs per kiloparsec. So again, you bring a scale into the problem. Or you can build up some interaction in the dark sector. You could have interaction between dark matter and dark energy, whatever you want. The point is that you bring a scale into the problem. And actually, as I say, you name it dark matter, because I think there are more models outside in the world for dark matter than people working on them. Okay, some people have created more than one model, so we have a plethora of those models. But there's an elephant in the room. Okay? The elephant is that we look at galaxies on one side and we look at cold dark matter simulations on the other one. But of course, they are connected by galaxy formation. So the first question one has to ask, can galaxy formation break the self-similarity? If the answer is yes, then we don't need to modify the dark sector. So how do you study galaxy formation? So what I want to present you is the results of a project that I have been working on I think it's now 10 years. It's called NIHAO. NIHAO is an acronym, stands for Numerical Investigation of 100 Astrophysical Objects, but also means hello in Chinese. And this is practically collaboration between where I am now, NYU Abu Dhabi, where I was before, the Max Planck Institute, and the Purple Mountain Observatory in China with Professor Xi Kang. So what we have done in NIHAO is try to build a large library of simulated galaxies. Why large library and of high resolution? So you need high resolution, as in this image here. This is one of our galaxies. You only see the stellar light here. You need high resolution because I told you all the problems are on small scales. And so you need high resolution, otherwise you don't resolve the small scales. So 100 parsecs. Why a large library? Well, if you want to study something that breaks self-similarity, you need to have statistical sample, right? You can't break self-similarity with two objects. So at the moment, we have more than 200 galaxies. This 172 is a bit outdated. That's the physics we have in the simulation. It doesn't really matter. I'm happy to give details if people are interested. We have AGN feedback, supernova feedbacks, the feedback for star formation, and so far, so on. The whole point is that now we can follow at the same time, in the same simulation, the formation of dark matter density. That's what I was showing you before, but also the gas temperature and the stellar density. All those simulations that we run, they're zoom simulations. So by every run, we get one galaxy out of it. Okay, so we can achieve very high resolution. I think it's the largest sample of high resolution galaxies available on the market. And also we scan the whole range. So we go from dwarf galaxies to massive ellipticals. Okay, so what you see here on the left is dark matter, color-coded by density. Middle gas, very simple color coding, red, hot, blue, cold. And on the right, you have stars, which are color-coded by density and age. For example, you see here the formation of a disk galaxy. We got extremely lucky in the simulation because we put the camera at some random angle and happened to have the disk perfectly edge on. Okay. And you see the formation of the galaxy. So this is some PR thing. On the left, you have real galaxies. On the right, you have simulated galaxies with NIHAO. Given to our large sample, we can find practically counterpart for almost every observed galaxy, from interacting couples, top right, top left, grand design spirals, and we can also put dust. You see, for example, in the simulator on the right, top right panel, this is galaxy where we also have dust emission, obscuration, and so far, so on. There's one caveat, though, that when we do the simulations, we cannot do these from first principle. What do I mean? For example, how do we treat star formation? So given this, the resolution we have, which is very high, each of our gas elements has a mass of roughly 10,000 solar masses. What does it mean? That this is a gas cloud. And at a given point in the simulation, if some properties are satisfied, given temperature and density, you see the threshold bottom left, some of the stellar particles, star gas particle, will go part of it in stars and part of it in gas. Then, so we don't form a stellar particle. So when we form a stellar particle, it's not a single star, it's a cluster of stars. Right? The typical mass is 1,000 solar masses. This star cluster has an IMF. Given the IMF, we can count how many supernovae we expect. So part of the stars that go supernovae, they give energy. This energy goes back into the gas. And the gas moves to a new temperature and density. That's our star formation and feedback loop in a very simple example. Why is this an issue? Because this is star forming region. Okay? And this is one of our particles. So we encompass all the amazing physics that is happening here. As I famous Hubble picture, this is the pillars of life. It's here top in the center. We compress all this amazing physics in one single element. So the first thing you have to do, and actually that's what you have to ask to anyone who comes to you and talks to you about galaxy formation, how do you validate your simulation? So the way we validate our simulation is, for example, to make sure that our galaxies, or the blue points on the right plot, they live on the same relation as the real galaxy. So here, for example, is the famous abundance matching technique. If you don't know what it is, it doesn't really matter. The x-axis is the halo mass, total mass of the galaxy. The y-axis is the stellar mass. Real galaxies, they live on the gray relation. Okay? And blue points are our galaxies. So you see they stay on the relation across 5 orders of magnitude in stellar mass, 3.5 orders of magnitude in halo mass. Again, I can go through many of those plots. For example, on the left, what you have here is the Tully-Fisher relation, rotation velocity versus stellar mass. And again, here observations are in red, and NIHAO results are the black points, and you can see we get the slope, the 0 point, and even the scatter. Okay? Those are validation plots. Those are plots that tell me that the galaxies are realistic. We have many more. In fact, if I have to go through the list of NIHAO papers, I think we just published NIHAO 28. So this stops at 1021, so it's a bit outdated. There are tons of papers where we validated the simulations. Since we validate the luminous part, now we can look at the dark part. Again, that's just a comparison to similar galaxies. So can we break the self-similarity? And now I'm going to make long story short. The answer is yes. Galaxy formation breaks the self-similarity. So this is in a galaxy. It's called, the left plot is an observational plot, not from NIHAO, from Oman 2015. So the blue points are the observation of this rotation curve. And this rotation curve of IC 2574 is notoriously difficult to be reproduced by simulations in cold dark matter because it has this very slow rising part where dark matter likes to do straight up and then right. So this is the exact same galaxy run, so the exact same observational points, the red points, just different survey, and you have here the results of NIHAO. So what you have here, that's a simulation where I have only dark matter, and again, I cannot fit the observational data. When I add baryons, I run again my simulation, I get the blue line, and the blue line goes straight through the points. By no means we ever wanted to reproduce IC 2574. The reason is that I have 100 galaxies, I can find one which looks like IC 2574. So that's a plot on the right that shows you this breaking of self-similarity. So what you have is radius on the x. On the y, you have the ratio between velocity in dark matter and hydro. If the self-similarity was not broken, all those lines would just compact around 0, around 1. Right? There would be no difference. You see here, the self-similarity is broken in all possible directions. Some galaxies, they have lower velocity than dark matter, some others they have higher, and you see the diversity. Okay? Why that happens? The explanation goes back to a very nice paper by Ponson and Governato, 2010. What you see here is the gas distribution in a galaxy of a mass around 10 to 11. What you see here, there are two competing effects. Gravity brings gas to the center. The gas gets dense and cold. Star formation happens. Supernova explode. The gas is ejected. Okay? So what you see here, the gas is continually coming in and going out. Now, let's suppose you take in some amount of gas, and the exact amount of mass goes in and out. Naively, one would expect that what the dark matter will do when the gas goes in, the dark matter will move in, because there's a deeper potential well. When the gas goes out, given that dark matter now has a high kinetic velocity, will also move out, right, to reestablish the orbital, its orbit. Now, so one could think naively there is zero effect here. What happens that this is not true? And the reason is that I'm going to play the movie again. The reason is that the gas flowing in happens on a long time scale. And the reason is that happens on free fall time scale. The gas going out happens on explosion time scale. It's almost instantaneous. That means that one process, gas in, is adiabatic. The other process, gas out, is non-adiabatic. And now, as you will remember, non-adiabatic processes are irreversible, and they leave an imprint in the dark matter. That means even if I move the same amount of gas, 1 kilogram of gas in and out, the net effect is not zero. It's that the expansion is going to win. So the dark matter will move out every time there is a supernova explosion. And kick by kick, that's how you modify the dark matter profile. Now, what you can imagine, the different galaxies have different star formation histories, and so that's how you get the diversity. So, for example, the diversity can be expressed. This is the asymptotic slope of the density profile, which in cold dark matter is always -1, no matter what. And what happens in our simulations is that instead of being always around fixed numbers, this density profile, it fluctuates up and down depending on the halo mass of the galaxy. And here's the reasons that for some galaxies you reach a perfect sweet spot when you have a lot of explosions. For example, the blue points here are affected by AGN feedback. The point is that there's no self-similarity anymore. Everything moves up and down. Okay? So the same things happen for the satellites. I told you that the satellites, you expect always the same number of satellites. But again, when you plug in galaxy information, there are several effects that play in. So what you see here on the left is dark matter, and on the right is the stars. And now what you see here that in this simulation, not every dark matter halo is populated with stars. So if you look at the center, you have a concentration of dark matter in the center on the left and a concentration of stars on the right. If you look at the big satellite, here it is, you have its counterpart, the one that's coming from the bottom, its counterpart in stars. But if you squint your eyes, you see that the majority of the satellites are dark. There's no counterpart in stars for this satellite. And the reason that in order to make a satellite in dark matter, it's very easy. You just need some gravity. But to make a satellite in stars, you need to accrete the gas, you need to keep the gas there, you're fighting against the UV background, you're fighting against supernova feedback, and so on. So one more time, you break the self-similarity. That's why galaxy clusters have a lot of satellites, because we are talking that the satellites of the galaxy cluster are galaxies themselves, very massive. It's very easy for those objects to retain their gas and their stars. When you move down to the Milky Way scale, it's much harder to keep stars. And now when you move to dwarf galaxies, you have 0 satellites around dwarf galaxies. Okay? So it's very easy to break self-similarity with variance. There's just a way to quantify it. What happens that here you have, as a function of the halo mass, the stellar mass of satellites. You see here 2 branches here. The top branch, which is marked by this arrow, is with the satellites they have stars, and you see they are on a kind of scaling relation. And then you have satellites that have 0 stars. They just put here on the bottom an arbitrary position. And this line here that crosses the plot, this is the dark fraction. So that's the amount of satellites that are dark, no stars, versus the amount of satellites with light. And you see that when you go at lower masses, satellites tend to become dark. Again, very easy to break self-similarity. That brings me back to my initial plot. What were you looking at? Well, the answer here is you were looking at the dwarf galaxy. In fact, if I show you now the stellar counterpart of this object, it's this. It's a little smudge in the center. This object has a dark matter mass of 10 to the 9. That's an ultra-faint galaxy. And now what you see is only the center has been able to make stars. Everything around is dark. If this was a galaxy cluster, you will see that each and every of these density spots here on the left would be lightened up with stars. Okay? So it's very easy to break the self-similarity. This is a very extreme object, has a stellar to total mass 10 to the minus 5. Okay. Problem is that those issues or cases have been solved in the past, but yet there is always a tendency from many observers to try to come up with new unexplainable observations. And I want to bring you just one example before concluding. And that's the reason is that people feel that they have to prove cold dark matter wrong. And now I have spent the last 10 years of my life trying to show people that there's nothing wrong with cold dark matter. It's a perfectly fine model. So the last issues that were brought to the public is the case of galaxies without dark matter. If you're not familiar, that's the paper that made quite an interesting splash in the field. It's a Nature letter by Peter van Dokkum, in which he found the galaxies that allegedly has zero dark matter. And after finding the first object, he found the second one in a follow-up paper. So let's have a look at this object. So this is the object, NGC something, Dragonfly 2. And you can measure the stellar mass, it's roughly 210 to the 8. And then what this galaxy has 10 globular clusters. So what you can do, you can use the velocity dispersion of the globular clusters to estimate the total mass. The dynamical mass, very simple, is the velocity dispersion of the globular clusters times the radius divided by g. So the radius, if you know at which distance is this object, there's been some debate in the literature, but we'll not enter into that. So the radius that is encompassed by those globular clusters is roughly 9 kiloparsec. So if you plug in the velocity that was found, 5.8 kilometers per second, 9 kiloparsec, and g in the right units, you get the total dynamical mass, which is 210 to the 8. Now what you can see, the dynamical mass is identical to the stellar mass. Okay? So in this object, there's no need for additional mass. There's no need for dark mass. So the question I had in mind, can we form an object like that in cold dark matter? So the first answer I got was no, because this is a plot where you have as a function of stellar mass, the velocity dispersion of the stars computed a la Van Dokkum. So choosing 10 random points into the galaxy and assuming those are globular clusters. And what you see is that in cold dark matter, for a stellar mass around 10 to the 8, you expect a dispersion velocity of around 25-30. The points you see in the bottom with the horizontal arrow bar, those are the measurements from Van Dokkum. There are 4 points, even though there are only 2 galaxies, and the reason that he has 2 methods to compute the velocity dispersion. So every time you will see 4 data points, even though there are only 2 galaxies. Just to be fair, I put everything. In fact, you see they are exactly the same stellar mass. There's only 1 measure for the stellar mass. He has 2 measurements for the velocity dispersion. Okay, so clearly, if you have to look at this plot, the simulations, which are all the points with the vertical arrow bars, they're very far away from the observations. So that could be a real issue. But the bad is that this galaxy the galaxy on the left, NGC Dragonfly 2, doesn't live in the field. It's a satellite of a much bigger object. This is the very massive elliptical galaxies in this plot here. So the first question, the first idea that can come is, what about tidal arresting? Okay, the small galaxy is going around the big galaxy and might have some of its mass removed. Here there is an issue though, it's that you can compute the tidal radius of this galaxy. So the tidal radius, which is the red circle here, is the radius within which you are safe. So you will not be removed by the tidal forces of the main object. And if you're outside the tidal radius, there's a very good chance that you as a star or dark matter particle will be removed by tidal forces. So the tidal radius is much smaller than the 14 kiloparsec that Van Dokkum used to compute this velocity dispersion. So he comments about that in his paper, and he says, look, the tidal radius is so large that it's the radius we use for observation, it's safe, right? It's well inside the tidal radius. I should not expect any tidal arrestment. Well, but that's not the whole story. Since I didn't kind of believe this explanation, I started running simulations. That's what I do for a living. So what I did, I took There's three galaxies on the left plot, which are color-coded, red, or orange, and blue. And I threw them against a big galaxy, which is the same as the elliptical in the center of this group. So here the galaxy is coming to the right, it goes close to the central objects, and then does one passage and it coming back. So what happens to the velocity dispersion in this case? Well, the velocity dispersion of the stars, clearly it's disturbed by this encounter. But how much is disturbed? A lot. In fact, what you see here is the change in velocity dispersion as a function of time. That's an arbitrary time of the orbit. The orbit takes about 2.5 gigayears to be completed. And what you see, the velocity dispersion starts at some number and then steadily decreases as a function of time. And decreases so much that emits the observational points that are here. Those are the 4 points from the Van Dokum observation. So how comes that the velocity, I can show you, these are the observational points, and I told you there are 4. I put them at arbitrary time, otherwise it would be collapsed all of them at the end, but just at arbitrary times just to show them. So the question is that how comes that you think the stars are protected by the Tidal radius, and instead they get removed? Before going into an explanation, I can show you that I play with the orbits. So different galaxies, they do different things. For example, here G1, I sent to an orbit, and there was a change in velocity dispersion, but it's very small. Where G3 and G2, for a given orbit and properties of the galaxy, they both create a galaxy with a total circular velocity dispersion of about 8 kilometers per second. Remember, they all start around 25. That's what you expect from quantum matter. So how comes? Well, the problem is the following, that you think that everything which is inside the tidal radius is protected. So let's look at the second panel. What you have is a dark matter particle, which is within the tidal radius. So you would expect that this dark matter particle is safe inside and will never be touched. Okay, similar to the stars. But the dark matter particles, stars are confined in orbits in the center. Dark matter particles, as they come from cosmological accretion, they have orbits with very large excursion. If you look at the orbits of a dark matter particle, it looks like a pretzel, the typical German piece of bread. And in fact, if I look at this particle which is moving, this particle most likely has an orbit like this. That means that this particle is not staying in the safe place within the tidal radius. Most likely it's moving outside the tidal radius. What happens? It happens that when the particle is, for example, in that position, it might be removed by the tidal effects of the other object. And in that case, you think, well, you're only changing the mass outside the tidal radius, right? If I remove the particle here, what is changing is the mass down there. But this particle was meant, after being removed, was meant to go back into the center. So if as time goes by, the net effect is that the mass in the center is affected. Okay? Because this particle, which was supposed to go back to the center, because another particle is going out and keep the mass in the center, is not coming back. So what's happening here is that kick after kick, the dark matter content, even inside the tidal radius, even inside the protected region, it's lowered. On the contrary, the stars, since they only stay within the stellar radius, they're always there. So what happens that passage after passage, kick after kick, the total velocity dispersion goes down, and so you have galaxies that start with a velocity dispersion around.
One second. What about the other particles that are outside and that they should stay outside, they get inside because of the same effect?
So practically what you have in an equilibrated dark matter halo, you have a continuous inflow and outflow. The net effect is 0, so the mass in the center is stable. So the particle, it's going out, another particle is taking its place. Then when this particle that took its place goes out, the original particle is supposed to come back to keep the mass constant. But this particle will never come back. Okay?
But you have other things that they should, because, I mean, this is true if you have an isolated thing. Okay? Now, if you have a tidal force on one side, then you will perturb not just the same center, but also the other particles from the other part, which may take some particles that will never reach the center to go into the center.
Right. It's the same thing. You're just looking for different angles. Yeah. So what happens that even if you only touch particles outside, let's say 15 kiloparsec, you're still affecting the inner 7 kiloparsec because you are preventing the new supply of particles. Okay, so practically there is a safe region which is within, let's say, 15 kiloparsec. And if you are inside as a star, you will never go outside. But dark matter is keep moving. And that's why sometimes some particles disappear. And then
I understand why the particles get out. But again, I think that you may have effect of other particles that will never go inside.
Right.
Because of this will go inside.
No, the tidal stripping, I mean, you have orbits perturbation, but tidal stripping is mainly an unbounding process. So since it's mainly unbinding process, particles once unbound, statistically will never go back into the center.
I know, but you have the other ones that will go this way, and because of this effect, they can go inside.
That's very minimal effect because we check the total mass in the center as a function of time, and it's definitely decreasing. Okay. So you think it's some particle that's scattered in, if you wish.
Yeah, scattered in.
Yeah, but it's very rare phenomenon because your gas is moving, so you want those particles to be scattered in a particular place. So scattering out is very easy. It's just an entropy reasoning, right? Scattering out is very easy because you make the particle unbound, so you just kick them. To kick them in, you have to kick them in with a precise velocity, and that's why it's a less likely process. It might happen. I haven't looked into that, but
because I can understand this mechanism for the smoothing of the perturbation for hot particles, for example. This works. Okay. But in this case, I mean, you have to check the particles that are outside.
Well, I can give you. This is the dark matter over stellar mass ratio, and you see this is the pericenter passage where the peak is, and you see that you do have some kicks here and there, right? Those are just pericenter, but you see that in general it's a downhill slope. It's a downhill slope. So that's the integrated amount. This is the dark matter mass inside 7 kiloparsecs.
So considering all the
everything.
Not just the single thing.
No, it's just the whole thing.
Okay.
So bottom line, it's quite easy to explain also objects like those. In the sense that it's true that if you look just at the simulation, you have that the expected velocity dispersion is 25, 30, which is much lower than the 7, 8 found by Van Dokkum, but tidal arresting can explain this easily. Now, there was a follow-up paper by Olga Moreno in which he showed that not only this happens, but it happens the right amount of times. So he used a combination of large-scale structure and starting from our idea, and he showed that you get roughly the right amount of this low dark matter content galaxy in galaxy clusters. You expect to have 2 to 3 in every object. That's based on cosmological. Because what we did here is just to show that it can be done. And now the statistics, it's also true that we only have 2 observed galaxies, so it's very hard to make statistics with 2. But it's possible to form those objects in cold dark matter. There's no real, so it's not something that challenges cold dark matter. So I am practically done. So my conclusion, I say partial because I have the second part of the conclusion, is that I personally do not see any observational need to move beyond cold dark matter. That doesn't mean we shouldn't explore other venues. But I hate when I read in papers that people start, because of this problem, we should look into self-interacting dark matter. Look into self-interacting dark matter, be my guest, no problem. But there's no problem here. There's no small-scale crisis, nothing like that. Everything works quite nicely. And it's true that we can't explain everything perfectly. Right? For example, the diversity that I was saying of galaxies, seems there is more diversity in galaxies than what we make in our simulation. But I don't think that's a problem for the cold dark matter. That's a problem, it's a challenge for our understanding of galaxy formation. I told you at the beginning, we have to compress a lot of incredibly interesting physics into very simple mechanisms. So all remaining issues, and I'm not saying they're unknown, they are all most likely related to our inability to fully capture galaxy formation. But before touching the dark matter backbone, one has to have a much better understanding of galaxy formation. That also includes galaxies without dark matter, which has been the last challenge brought up. But there's a challenge every 2 months to cold dark matter. And I don't have time to explore all of that. So then it's cold dark matter. No, not at all. By no means. From the point of view of galaxy formation, there is no reason to have cold dark matter. With cold dark matter here, what I mean is the WIMP model, the models that people nearby here at the Grand Central Laboratories are spending tons of money to try to find with the Xenon experiment and others. There is really no indication for that. In fact, if you just want to understand galaxy formation. You don't need the WIMP-like. WIMP, I mean an object with GeV mass or even higher. Anything which is not too warm, so any particle which doesn't have an initial velocity which is too high, which creates problems for structure formation, works like a charm. And the limit is 5 keV. So you have 5 keV, that means you have 50 keV, 500 keV, 5 MeV, 50 MeV, 500 MeV before reaching the GeV. Right? So you have a huge plethora, a huge dynamical range for dark matter mass between what is needed by galaxy formation and what is looked for by particle physicists. And that's, in my opinion, the most worrisome thing at the moment. Everybody's looking for one kind of particles, but there's no push from galaxy formation point of view. So just to summarize, cold dark matter is not wrong, but does not imply by any means that it's the right model. Thank you. That's it.